including yourself.
And then lastly, we're going to present the approach and the preliminary results that we have of the benchmarking that we did of the SASE 2010 MSM, which is being used for the sensitivity studies that we're doing for the SSI and SSI analyses. Okay? And so that's all I'm going to say. And then I'm going to turn it over to Lubin. Lubin's going to go through a lot of the work that Shimzu and GEH are doing for us, for Seismic. And you all know Lubin, right? Podolsky? Okay. And then Alidat Hashemi, you guys know Alidat? And he's going to cover the RAIs that Bechtel's working on for us when we get there. Okay? Yes.
Did anybody else join the phone call after introductions? Please.
Hello, can you hear me?
Yes.
This is Erica Gray. I'm calling from Henrico, Virginia.
Good morning.
Morning.
Harry, can I ask you one question, too, a logistics question? Are you all thinking that we're going to go from 9 to 1? Do we have all 4 hours, or do you?
We have all 4 hours. We can go over if we need to.
Okay, great.
We may have to scramble after 1. We'll try to figure something out during the meeting, but we can go right through. We can make it a working meeting and work through lunch.
Okay.
Whatever we need to do.
Okay, so when we get closer to that time, we'll work out the details.
Yeah, exactly.
Okay, great, thank you. So now I'll turn it over to Lubin.
Good morning. I will try to give a brief overview of the sections that they have changed. I mean, they're describing the seismic analysis and design. Basically, we had to do to address the exceedances of the first. We performed site-specific SSI analysis of the 3 Category 1 buildings. This is the reactor building, field building, control building, and fire water service complex. The SSI analysis are performed following approach which is consistent with the DCD and Fermi-Cola, which was already submitted. And also we have, for that we use SASE 2010 computer program, which is update of the SASE 2000. We use the site-specific input ground motion and properties that are documented in exercise section 3.7.1. And the models we use for the analysis, the structural models, are those documented in the DCD Appendix 3A. They only reflect a few changes. The mesh was adjusted, and the stiffness and damping properties of the concrete members were adjusted to reflect the Unit 3's conditions. These site-specific analyses provide the following results that serve as the basis for developing the design basis for Nortana. We get member forces because it's landmark stick model and maximum accelerations, and they serve as a loads, and they serve for reconciliation of the seismic design of the structure in the 3 sites. Then we have the time histories of the spring reactions, as well as structure interfaces that are used for input for the stability and dynamic bearing pressure calculations. Maximum spring forces at the exterior walls, soil interfaces provide the results for the seismic or dynamic lateral pressure distribution, and also the acceleration time histories for accelerations at landmass locations are used to calculate site-specific in-structure response spectra for different damping values. At this point, I want to point out that the EFSAR presents in-structure response spectra only at selected locations, those are the same locations that are presented in the DCD, but the in-structure response spectra is developed for all locations because they serve for design purposes. More details about the analysis and sensitivity studies are documented in the technical reports, which will be available for audit. This is like a brief discussion of the model we used and what we consider for the analysis that are presented in 3.72. We use a model that is partially embedded in situ rock And in order to take in account the concrete fill, which is around the foundation, we include that in the finite element model. The effects of the soil above the rock and the fill concrete are not taken into account. So we make the assumptions that they can be neglected. The next slide.
Mute on.
The difference between the reactor building, fuel building, and control building model is that we have the rock embedment is shallower, and also we have fill concrete below the foundation. So that is between the foundation and the rock strata below. And also we have make the same assumption about the soil not being important for the response. This is the model of fire water service complex. This is basically a surface-mounted foundation, and below the foundation there is a block of concrete fill that, and basically the whole building is supported by rock at the end. Below the concrete fill. In the South Sea analysis, we considered the in-situ soil properties around the concrete fill and below the rock, and the concrete fill is the part of the finite element model, structural finite element model. I will go to the next slide. Now to reconcile the structural design for the standard for the Unit 3 conditions. Basically took a conservative and simple approach where we used scale factors to calculate the stress demands and for Nortana. Basically for all loads that we calculated, we see which one has the maximum exceedance from the DCD load, and they multiply the stresses for this scaling factor, and then we compare that with the allowable stresses. And for the cases where we come and then we can, using this conservative approach, we find out that the stresses are higher than the allowables. We go a little bit more refined analysis where we look what is the contribution of the seismic stress to the total stress, and that's how we adjust it to show that still all the stresses are below the allowables. And basically to demonstrate that the standard design is applicable for Unit 3 sites. I mean, this is for the structures. The next slide. Unlike the structures, for the in-structure response spectra, we observed exceedances as shown in this figure, which is a typical one, where the responses from the site-specific analysis exceed the design, DCD design in-structure response spectra for a range of frequencies. So in order to, maybe the next slide, in order to address this issue, we have developed a new set of site-specific design in-structure response spectrum. That is for all locations, so they will serve for qualification and design or evaluation of the equipment and components in all 3 buildings at all locations. Next slide. Besides this, we calculate also the lateral pressures. What we present in the FSAT, according to the SRP requirements, we compare the total pressures, static and dynamic. The dynamic pressures are obtained from two types of analysis. The first one is from the site-specific SSI analysis. They're taken directly from SASI, and we calculate the pressure distribution. Also, in section 3.8.5.5.1, we perform sliding stability, where we need resistance from the concrete field to satisfy the sliding stability of the building. We take that pressure and we compare that with the loads that we have considered in the standard design. For the static and hydrostatic pressure, we use Nortana site-specific parameters like soil properties, here rock properties, as well as elevation of water table for a buoyancy effect. So, next slide. This is a typical figure for the 2 of the 8 walls that we have considered with the pressures. I want to point out the reactor building, fuel building, and control building are the ones which are embedded. As you can see, for most of the height of the wall, the DCD loads exceed the loads, the site-specific demand. And now, in order to address these exceedances, which are sharp and really appear in the small depth, we have performed site analysis to show that the resulting moments and shear forces on the walls are smaller than what the DCD was designed for, the standard design. So basically, this demonstrated that lateral pressure demands are also enveloped by the standard design. In section 3.8.5.5.1, we did a foundation stability analysis for the site-specific conditions. Those analyses are based on the results that we got from the site-specific SSI analysis and using the site-specific parameters as a groundwater level, friction coefficients, and so on. The methodology we are applying is identical to that used in the DCD with some assumptions which are conservative. We used 0.03 second moving window average on the SSI reaction time histories used for the sliding evaluations, and there was RAI questions regarding this. So I will give more details about this later when we talk about the RAIs. I want to point out that the reactor building, fuel building stability neglect the resistance provided by shear key, and basically those shear keys are not needed in the unit 3 sites for the sliding stability. We calculated very large values for the overturning stability. Now for the sliding stability of the reactor building, fuel building, and control building, we needed to rely on the lateral resistance from the concrete field. But the resulting pressures and forces we get are very low, and that don't compromise, as we showed before, either the structural capacity of the walls of the structures or the capacity of the concrete field and the rocks surrounding the building. For the fire water service complex, we need to consider the shear keys, the resistance from the shear keys, which are, I want to point out, embedded in the concrete field below. So those resulting demands of the shear keys are smaller than what was considered in the DCD. So basically, the standard design of the shear keys is adequate for the Unit 3 site conditions. The last calculations that we did are to calculate the site-specific values for the foundation dynamic bearing pressures. Basically, we use the site-specific parameters, the SASI analysis, pretty much same methodology for consistency was used also for the bearing pressure calculations. What I want to point out that in the table below gives the values of the dynamic pressure and the maximum dynamic pressures in the DCD, which are the ones considered for the design. And those are obtained from from analysis in the DCD of all generic subway conditions, not the hard rock, which might be the closest to the Nortana condition. With this, we have concluded the overview. I mean, most of the questions we have had in the RAI circle will be addressed later. But if you have any other question, then we can.
got many questions over the material.
So we can go through our eyes and then, okay, thank you.
So now this piece is where Lubin's going to talk about the changes that we made. We had mentioned these to Shindu. I had talked to you briefly about them, right, several weeks ago, telling you that we're going to be submitting this letter where that's our changes. Okay, so that's what this piece is about. It's going to talk about the changes that are in this letter that we submitted yesterday. Okay? Do you want a copy of this?
No, nothing.
Okay.
Yes, cost.
Okay. All right.
Now, we are on slide 17 for the people who are on the phone, or 18. I apologize for not mentioning that. Now, we had made a couple of changes since the FSAR was submitted in December, and basically they are related to these items. First, we found error in the stiffness and damping properties assigned to the reactor building fuel building model of exterior walls and some circular reinforced members to adjust them for the actual stress level they experience under unitary load demand. As a consequence, we reperformed the analysis on the corrected model, and we had to change all the tables, figures, and text to present the new results, which are related to item 1 above. Also, we changed all the instruction response spectral results that are presented in the FSAR have been modified to reflect the use of the revised methodology that we for addressing the coupling effects between the flow rotation and rocking and torsion. And also we changed the text in the FSAR to correct the error made in the calculation of later of the stability of the fire water service complex, where we accounted for the later resistance from the engineered field placed around the foundation. And also we found a few editorial and transposition errors in the results, and those have been corrected. I mean, majority of those were corrected in the markup that was submitted yesterday. I want to point out that the changes made to the FSAR only affect some of the descriptions and some of the numbers, but have no effect on the final conclusions of what was presented in the FSAR. Now it's slide 19. Yeah.
Excuse me.
Yes.
Maybe could we use the phone? No. I just want to make sure the people on the phone can hear you.
Well, I have a question. You talked about the revised methodology for computing ISRS.
Correct.
Is that revised relative to the DTE methodology? Or is it that you just apply the DTE methodology before? Tells you how to compute the ISRS.
I mean, we follow still the DCD. They say that actually that there were two types of approach you can use. You can combine the instruction response spectra both in SRSS or in time domain. And now we are what was applied before, and I will have slides. It was a mixture, so maybe it's better when we go through I have the actual equations to tell you what is the difference. So basically, now on slide 19, I want to give you an introduction how we address the cracking to get to the best estimate properties assigned to the reinforced concrete members. Basically, we use 50% reduced stiffness and necessary damping for all exterior all shear walls and exterior walls where the in-plane shear stress exceeds the concrete rupture stress, which is 3 times square root of the compressive strength of the concrete in PSI. The same, we apply 50% reduction stiffness on the SSC damping for the oscillators and the stick and outer wall shell elements if the outer plane bending stresses exceed the the cracking moment criteria of ACI 349. Now, to evaluate what are the stresses that satisfy the stress threshold criteria for the shear walls, we use effective area, which is 60% of actual area of the shear walls in perpendicular direction. And for the circular section, we use 50% of the total area. So basically, we have half in one direction, half in the other horizontal direction. If we can go to the next slide. Now, basically what we have observed that we applied 60% reduction to the shear area to the circular elements, and that affected some of the base estimate properties. Basically for wire water solid complex, there was no change. All of the elements remain uncracked, and we used OB damping. So the fire water service complex, the stress levels are fairly low, so they don't crack. For the control building, there was no change also because there's no circular elements, and we used still, as it is presented in December, some a version of the FSAR. We use crack stiffness and SSE damping properties to all members. Now, the changes were made on the reactor building model. First, full uncracked stiffness properties of damping are assigned to some stick elements of the circular elements, and I will show a figure example where that changed. There are a few of them that were affected by this. And also, we found error that we didn't apply reduced crack concrete stiffness assessed to the shell elements that model the below grade exterior walls. Next slide, 20. Right. This slide shows the example of, for example, on the left-hand side you have the model which is documented in the FSAR revision from December, and then the changes in those elements which are in the containment. We can go to the other side. So in order to address these errors, we corrected the model for reactor building, fuel building, and we perform analysis. The results of those analyses show that the effects are minor. I mean, some numbers change, but as I said before, there was no really difference of what we had observed as behavior. The structures, loads were affected a little bit, but not as much to exceed the standard design capacity. So one of the two examples are the pedestal walls slightly increased, but we have demonstrated that the stresses are below the allowables. Same is for the vent wall and RSW. So those are like three locations where we look for some changes in the calculation. The same applies for the plots presenting the total pressure distribution, which are in the figures 3.8.4, 201 to 204. I mean, those are hardly to even notice when you compare both of the figures. They are still below the demands. They are enveloped by the standard design. We were looking and the increases in the lateral resistance forces we need on the exterior walls from the sliding evaluations. Those increased for less than 6%. And also we saw some increase in the magnitude of the maximum dynamic bearing pressures, very minor, below 4%. But the tables documenting these results have to be changed to have the correct values there. Slide 24. Now the revised methodology for the structural response spectra, the question we had before. Now, just as introduction, the Stasi analysis are performed in a manner that the ground motion excitation is applied on the model in 3 directions, independently. So after that, getting the responses from these 3 sets of analysis, we combine them, and we use either time domain algebraic sum or the square root of sum of squares method. So maximum nodal acceleration and displacement I combine using the SRSS method. The same applies for the maximum member forces, moments, and the maximum lateral pressure results. For the stability evaluation, consistent with the DCD methodology, we combine the responses in time domain. So for each time we look what are the forces. Now for the structural response spectra, we are applying the time history. We use time history results. We calculate the responses at the edges of the floor, and then we use SRSS method to combine the responses due to the 3 earthquake components. And I will discuss a little bit further, but this is the only change in the methodology we applied regarding how the responses from the different earthquake components are combined. The next slide, 25.
Does that answer?
No, we have more about it. Right, there is a details more. Basically, from this Stasi analysis, we calculate 6 time histories at each landmass location, 3 translations and 3 rotations. What we did before, this is for the December submittal, we calculate the response spectra for all of them at the edges, and for rotation and translation, and then we use absolute sum to calculate horizontal structural response spectra, and this absolute sum in frequency domain, and we apply the SRSS method to calculate the vertical structural response spectra. And the application of SRSS method for this kind, for combining rotations and translations, does not follow the regulations, and that strictly stipulate that the SRSS method is to be used for combination of the responses due to the 3 directions of the earthquake. So basically, we went and we made correction for this error. In the next slide, what we did, we went in time domain and we calculated the responses at the 4 edges of the floor by using the equations I have presented up, and I will give you the first index notifies the direction of the earthquake, and the second index notifies the direction of the response. So those are the equations we are using to combine translations, rotations, and to find responses, time histories of the responses at the 4 edges. The next slide. Yes.
Plus minuses. So the plus minus is parentheses means that you're considering the ground motion going this way or going this way.
I mean, yes, or basically you get two corners. They will have for the horizontal. They can go either way.
And the plus minus in the two terms is for the exposure or the bending going this way or going this way.
Correct.
So once you compute each one of those, for example, you compute the first index is what? The response, and the second index is the seismic front, right?
No, it's the other way around. Right.
So you do SRSS of AX, AX, Y, and AXZ.
The next slide will show what we will have.
Okay.
Yeah. Basically, we calculate response spectra now for each edge from the results we showed before in the three directions, I mean the three translations. And in order to develop instruction response spectra for the whole walk, we envelope